Now, let's talk about an alternative implementation with something that I think most of you have not seen yet, and it's called an impedance or an admittance inverter. So it turns out that this ladder implementation we've seen so far, meaning the idea of having series and shunt elements right next to each other, is perhaps aesthetically pleasing, but is not the most convenient way to build things in real life. In fact, it turns out, and this is something we'll understand more and more as we talk about bandpass or bandstop filters, that I like to have only a single element to work with, either series or shunt, but not both. And the reason for that is because when I basically work on implementing these elements, for a bandpass or a bandstop, I'm not going to have simple inductors and capacitors. I will actually end up having resonators. And when I have resonators, it's actually a very difficult thing to implement a high-quality resonator. It's a big deal. It takes a lot of time. It takes a lot of money. And once I implement one resonator, I don't want to now go and implement another one that might be a shunt resonator if I did a series one. So the way it works in real life is that you implement only one type of element, series or shunt, and then you basically realize your topology. So the way that we basically get around this annoyance that we have so far is by using this key device, which we will see many, many times, called an inverter. So an inverter is a mathematical construct that basically says that all that it does is that it inverts the impedance, as its name says. So in other words, if you take a load and you put an inverter in front of it, you will basically end up with an impedance that's simply 1 by ZL times some value k that depends on the realization of the inverter, k squared actually. And the inverter will also have a phase shift, plus or minus 90 degrees. And this works actually both in the impedance domain as well as in the admittance domain. So clearly not just ZL will be inverted, but YL will be inverted as well. And so in order to avoid saying constantly impedance or admittance inverter, I'm using often the word immittance inverter, or simply I will say impedance inverter, and you will understand that admittance inverter is the same as well. Now, even though this might appear a relatively strange element, particularly if you've never seen an inverter before, it turns out that it can actually be realized quite easily. So I'll show you the realization in a minute. This is, by the way, the ABCD matrix of the inverter. So here is a potential realization. So just a quarter wavelength transmission line, whose characteristic impedance is simply K, or characteristic admittance is simply J, does exactly what the equation basically says here. So, and this is something we've proven before. So if you plug in a load here, ZL, you will basically get K squared divided by ZL. However, one key difference of an inverter in theory compared to this very simple realization is that this one is bandwidth limited, meaning that this one works only for the frequency where the transmission line is lambda by 4. And the minute you move slightly below or above that, it doesn't invert anymore. The theoretical construct of an impedance of an admittance inverter is that it does this from DC to light, from 0 to infinity. Unfortunately, such things don't exist. And so you will see right now the first limitation of this technique. So yes, an impedance or admittance inverter that has the ability to invert things, as you'll see soon, will allow us to only have a series or shunt element, but at the cost of limited bandwidth. And the first bandwidth limitation you're seeing right now is going to be at what frequency does this thing work? And for what kind of bandwidth does this thing work? Now, realizations of inverters are not just done with transmission lines. People have invented other stranger elements that do exactly the same thing, some of which I'm actually showing you right here. So, for example, this very first element is something that includes a transmission line. Here you can see the electrical length of the transmission line, and then it includes a shunt inductor. Another case, it actually includes a transmission line left and right, and then a series capacitance. Or you may include a T network here or a pi network here. But what is interesting to realize here is that there is always something annoying. What the annoying part is, if I look, for example, for the T network, is that I need these negative capacitances. I don't know about you, but last time I tried to buy one of those, they didn't exist. Also, if you look at the pi network, it has exactly the same problem. And if you look at the very first realizations with the transmission lines left and right, they actually come with negative electrical length. So again, you can't easily buy such a transmission line. But here's what happens. Thank God, these type of negative transmission lines can actually be absorbed in positive transmission lines. So in other words, an inverter is almost never realized by itself. What will happen is that we will have some type of a transmission line on the left-hand side and some type of a transmission line on the right-hand side. And these type of transmission lines will actually have a positive electrical length. For example, maybe this one here will be 90 degrees. Maybe this one here will be 90 degrees. Maybe this thing here needs to be negative 15. Maybe this guy needs to be negative 15. So when you build the whole thing, you will actually build something that is 75 degrees. And then it basically suddenly it will work. Right? So that's how we basically deal with this. Similarly, we will select an inverter that might look like this pi network you see here, but right next here and to the right here, we will have positive capacitances that will absorb these negative ones. And so that's basically the trick for proceeding with these networks that, again, in the beginning may appear a little bit strange. So once we go with the prototype synthesis, which we will do in the next section, the network will look the way you see it right here. So either it will have only the series elements, as you will see here, and before and after every series element, you will see an inverter, or it will have only the shunt elements, and again, before and after, you will see an inverter. So what are the benefits of going through this? I already mentioned one of them, which is the idea of using only a single type of an element. But there is a second significant advantage, and that is actually highlighted right here. With the synthesis technique that I just showed you, we were basically locked in very specific values. For example, we came up with an element of, let's say, G3 that had to be equal to 1.9843, and that meant when you translate this to an actual capacitance or inductance, you have to go and buy this. Or this times a normalizing number once we denormalize from 1 ohm to something else. Well, you can't buy that. So what are you going to do? If you can't buy that, either you have to build it. And yes, if you make all your devices custom made, maybe you can do this. But then again, it becomes annoying because you're never going to hit exactly that number. Or you have to basically go and buy it and make compromises. For example, I will buy maybe a 2 value, I don't know, 2 henries or 2 farads times the denormalization, but this could be plus or minus 20% or plus or minus 10%, depending on the tolerance, and basically then I have issues. The fantastic thing about this implementation is that the values of your actual components are totally arbitrary. So you choose what you want them to be, and you scale everything based on the value of the inverters, which is actually a much easier thing to do. So your actual elements in the filter can be any value you like. So somehow maybe your factory is producing inductors of value 2 nanohenry, and that's all you can do. Great, you can actually build a filter based on that. So this is a real advantage, which is not just true for the low-pass prototypes, but particularly for the band-pass filters or the band-stop filters, which again, we're building resonators, and there we have to control the impedance of the resonator. And a lot of times, the impedance of the resonator, which is the equivalent of saying now here the value of 2 nanohenry, is something that we have limited control over based on our fab process. So if you always have to control the impedance of your resonator based on the previous synthesis technique, your life is much harder. So that's really the main 2 reasons why, despite the fact that the inverters have limited bandwidth, we actually prefer this approach versus the first one, which is, I would call it the undergraduate version of filter synthesis.